Good morning, dear students. In the last class, we came to know how to represent this vibrational motion. So I told you that these vibratory motions are the sines and the cosine waves. So the basic equation of vibration can be represented by this equation: x equals to capital A sine theta, or instead of theta you can write omega t. So where omega is the angular acceleration, small t is the time, instantaneous time. So capital A is the displacement of the particle or the system, so it is called as the amplitude. Okay, and here x is the displacement, which is a function of time. Okay, so this is the basic representation of a sinusoidal curve, which is simple harmonic motion equation. Okay, so in the last class, so we took the example of this spring mass system. Okay, so the spring mass system, when it will be oscillating with respect to this equilibrium line or mean line, so we will get this type of sinusoidal curve. But how these curves generally form, so today I will show you. So first of all, I will take the example of the pendulum. Okay, so as you all know that for a simple pendulum, the motion is simple harmonic motion, and in this introductory phase of vibration, so you came to know that the simple harmonic motion can be represented by this sinusoidal curve. Okay, so how this sinusoidal curve will be formed? So here you can see. So when, see, so this is the equilibrium position. Okay, so when the bob will move in this direction, means when you will first you need to displace this bob by giving some angular deflection. So when it will move to this position, so you will be able to see that the curve will be forming the quarter cycle. So in the back directional motion, reverse directional motion, so it will again form the half quarter cycle. Okay, means the semicircular curve you will get. It is not exactly semicircle, but this half portion you will get here when it will complete half of its way. Okay, or oscillation. Then again from this mean line in the reverse direction, from this point to this point, again it will be forming the next quarter cycle, and when returning back from this point to this point, again the lower half portion will be completed. Okay, thus it will complete one cycle. So you can see 1 quarter cycle, 2 quarter cycle, 3 quarter, then 4 quarter, then it will form a complete sinusoidal cycle. Okay, and time duration to form this curve will be the time period of vibration. Okay, and this displacement from here to here, or from this mean line to this point, that is the amplitude, maximum amplitude. Okay, so here in our equation we took it as capital A. Okay, but the example which we took in that particular slide, it is a spring mass system. But I have told you that in this particular spring mass system, so there will be a amplitude A, and there will be one angular velocity. Okay, which is omega.
Excuse me, sir.
Yes.
Sir, Raktim and Karan, they are requesting to enter the class.
No, actually, it is auto admitted. Okay. So I don't know why.
Okay,
Yeah, tell them that they will be auto admitted. Okay.
okay, sir.
Yeah, my voice is audible.
Yes, it's audible, sir.
Okay, please mute. Okay, yourself so that yeah, yeah, yeah,
Okay, sir.
yes. So the example which I took to make you understand this phenomena is a simple spring mass system. Okay, so how this sinusoidal curve will be formed? So you can see from this figure, see from this mean position, so when it is moving downward, okay, so that is one quarter cycle, okay, and from this downward point maximum, okay, amplitude, when it is again moving back in the reverse direction to this mean line, then this one half cycle will be completed. Then from this mean line again it will move to upside, okay, upside direction, then again it will come to this position, okay, then it will be forming the complete cycle, okay, when it will move back to the original position. You can see, okay, from mean line to the upward direction, so you will get this quarter cycle, then from the upward maximum upward position to the mean line you will get again this second uh, quarter, then you will get the third quarter when it will move downward, then the complete cycle you will get. Okay, the time period is t, capital T. So capital T equals to 2 pi upon omega. So here omega is the angular velocity, okay, but in vibration we will call omega as the frequency, okay, frequency in radian per second, and linear frequency is small f, which is cycle per second, okay, which is inverse of time period, or omega by 2 pi. Okay, so this equation of motion is represented by this equation, x equals to a sine omega t. So now you can ask me that, sir, why this sinusoidal equation is only in this form, x equals to a sine omega t. So what is x equals to a sine omega t? This is the locus of all the points which will be there on this line, okay. So you will get, if you put the value of t and omega, so you will get this line, okay, this curve you will get. So how this curve is formed actually? So to understand that, yeah, so I think this is visible. In the last Milo, actually he told me that in the video lectures, so it is little bit compressed. Okay, so what I will do, I will share these slides with you. Okay, don't worry for that. So as because the spring mass system, when it will be connected, you all know that that is a simple harmonic motion. So simple harmonic motion means there will be the angular constant angular velocity. So this circular this motion can be represented as an equivalent motion to the spring mass system. Okay, so in Stokes-Young mechanism we have seen that the spring mass system is the equivalent system to this circular system, okay, which is having a constant angular velocity. So let this circular motion is represented by this projection of this sinusoidal curve, okay, and how this circular wave can be represented by the sinusoidal curve. For that again I have one, yeah, so you can see, So this is also the second definition of simple harmonic motion, or you can say that when the acceleration, or you can say when one particle is moving in a circular path with a constant angular velocity, then the motion is a simple harmonic motion, and the simple harmonic motion can be represented by this sinusoidal curve. Okay, so this way the sinusoidal curve is formed. Okay, so it may be the example of simple pendulum, it may be the example of spring mass system. So every system which is in vibrational motion can be represented by some sine or cosine curve. Okay, so now we will see why the equation is x equals to a sine omega t for this type of circular motion, okay, or simple harmonic motion. So let us consider this mean line, okay, to be, it is, let's consider it is O, origin is O. Okay, here also the origin is O. So radius for the circle will be small r. This is the complete radius. This is omega t because this is theta, so theta equals to omega t. Let us consider the particle reaches this position, okay, P. So if you draw this projection here, so here this particle will be, okay, it will be from here, if you just draw this perpendicular, it will be qs, and from here if you draw the perpendicular, it will be pr. Okay, so here it will form one triangle opr. Okay, so these two lines, PR and QS. Okay, so this line are the perpendicular line from this point P and Q, okay, to this mean line. So this is the equilibrium line, and here also one reference line. It is considered as the equilibrium line. Okay, so how the equation is actually formed, so we will see. So here I have drawn the same drawing PR QS. Okay, so if you just compare this position, that is, what is this xt? Okay, means this is x, this is x. In vertical direction we will be calculating the amplitude or displacement. Okay, so this is x, this amount of distance, vertical distance is x, that is why it is written as x, as it is function of time, so x of t. Okay, so this PR, what is x of t? It is equals to qs, or you can write, instead of qr, it is qs, instead of you can write pr. Okay, qs or pr. So pr I have written. So what is pr? So as, because this is the triangle, okay, right angle triangle, and this maximum displacement is what? It is capital A. So in the last figure I have told you that this radius is r, but actually this point is r. Okay, so that is a mistake. So PR, so this is one point PR. Okay, and this radius is capital A, that is the maximum amplitude of the particle, so capital A. So what is PR? So by applying the trigonometry, so you can write that the opposite side of this angle will be a sine theta, because this angle is theta or omega t. So this is a sine theta. Okay, so this distance, so x of t will be equals to qs equals to pr equals to a sine theta. Okay, so a sine omega t. So omega is what? 2 pi upon t. Okay, so this way the equation becomes x of t equals to a sine theta or a sine omega t. Okay, so please remember this concept, because this is the basic equation of vibration. Okay, or same way that this is the basic equation of simple harmonic motion. So here capital T is the time period, small t is the instantaneous time. Okay, any time in this axis, okay, or in this mean line. So f, small f is the frequency, which is equals to 1 upon capital T. Omega is the radian per second, or it is called as frequency, though it is the angular velocity, but in vibration we will be calling it as frequency. Okay, so sometimes I will be calling it as natural frequency, sometimes I will be calling it as frequency. Okay, so its unit is radian per second, and f is the linear frequency. Okay, so if any problem is given in vibration, so by looking at the unit, whether it is hertz or whether it is radian per second. So you need to consider the frequency, whether it is omega or whether it is small f. Okay, so these points are important points. Now let us see what was taught in the last class. So I told you that this is the basic equation, x equals to a sine omega t. So if you double differentiate it, you will get the acceleration. If you differentiate it once with respect to t, then you will get the velocity. Okay, and in cos and sine function, how you will be able to write these equations, so we came to know in the last class. Okay, and to represent the displacement, velocity and acceleration in a common scale. Okay, so I showed you this diagram, that if this is the reference line, then this will be x displacement, where capital A is the amplitude, this is omega t, that is theta. Perpendicular to this, there will be velocity, because velocity leads the displacement vector by an angle of pi by 2, and acceleration vector by an angle of pi by 2. So acceleration vector is opposite to the displacement vector by the definition of simple harmonic motion, and mathematically also you can prove that acceleration is directly opposite to displacement. Okay, and it is proportional to displacement. Okay, so these are the very basic things of vibration. So we will be solving one problem today. Okay, on this concept. So let us see one problem. I think it is visible to you. Okay, so I will just read out this problem. So here you can see the motion of a particle is represented. Okay, motion of a particle is represented. Here this particle is represented by the equation. Here x is not written, so here you need to introduce one x. Okay, by the equation, x equals to 10 sine omega t. Okay, so 10 is the amplitude of motion, omega t. Okay, this is the theta. So initial displacement is this one, omega t. So the relative positions and magnitudes of the displacement, velocity and acceleration vector at any time for the case when omega equals to 2 radian per second and omega equals to 0.5 radian per second. Okay, so I think this is very simple problem. Okay, so what we have got the equation that x equals to 10 sine omega t. Okay, I think my screen is visible to you. Hello, anyone please respond. Okay, okay, the motion of a particle is represented. Okay, so this is our equation, x equals to 10 sine omega t. So we need to find out the displacement, velocity and acceleration, okay, at any time when we have got the omega 1 and omega 2. Okay, so our equation is this one. So first we need to find out the differentiation with respect to t. Then first differentiation will give you the velocity, second differentiation will give you the acceleration. So if you differentiate once, it will be x dot. So 10 omega will come out. So in terms of cos you can write, then if you convert it to sine, then it will be plus pi by 2, omega t plus pi by 2. Okay, so why it is sine omega t plus pi by 2? So in the last class, so we had discussed that concept. Okay, so in terms of cos also you can write, but to draw the graphical representation, so we will be using these similar trigonometric functions. So for acceleration also it will be x double dot. So 10 omega will come out, 10 omega into omega, that is omega square sine of omega t plus pi. Okay, so the magnitude of displacement, velocity and acceleration vector are 10 omega and 10 omega square. Okay, so these are the magnitude of amplitude. Okay, or these are the magnitude of displacement, the magnitude of velocity, this is the magnitude of acceleration. Okay, So this first coefficients which will be uh, in front of this sine curve will be the magnitude. Okay, this is magnitude of amplitude, this is magnitude of velocity, this is magnitude acceleration. So the phase difference is such that velocity vector, so here velocity vector leads the displacement vector by pi by 2, acceleration vector leads the velocity vector by pi by 2. So why we have written this? Because we need to represent this in the graphical form. Okay, so that is why I have added this line. Okay, so in case 1, so we were given the omega as 2 radian per second. Okay, so the time period will be what? So t1 will be 2 pi by omega 1. Okay, this 2, so 2 pi by 2, that is pi second. Okay, so you can convert it to decimal or numeric value, but here it is pi second, as because you were asked to find out the time period for each of the motions. Okay, so here for second case, so when you will put omega equals to 0.5 radian per second, so it will be 2 pi by 0.5. Okay, so it is 4 pi second. Okay, so it is not necessary to use this time period to draw this graphical representation. Only by the help of these three equations, so you will be able to find out the graphical representation, or to draw the graphical representation. Okay, so for the first case, so what was our equation? 10 sin omega t, means 10 was the magnitude of displacement. Okay, displacement equation, 10 as a magnitude of displacement equation to 10. So here the velocity curve will be there, or velocity line will be there, because pi by 2 is the leading angle with respect to the displacement. Okay, so at an angle of pi by 2, so we will be drawing this amplitude 20. Okay, so 10, so this will be shorter line, this will be longer line. Okay, by taking a just not the exact dimension, just we will be representing this graph. Okay, graphical representation. Okay, so this will be 20, as because 10 into, for the first case omega was 2, so 10 into omega, 10 into 2, it will be 20. So at an angle of pi by 2, so this velocity vector will be at an angle of pi by 2 displacement, then acceleration vector will be at an angle of pi by 2 to this velocity, which is having a magnitude of 10 into 2 into 2, because omega square. Okay, and omega value is 2, it is given, so 40. So 40, here the line, it is I think it is not this thing. Okay, so from here to here, one arrow mark you need to add on the end, left end. Okay, and this direction will be opposite to the displacement. Okay, so from this graphical representation, it is very much clear. Okay, that displacement is in the opposite direction of acceleration, and the magnitudes of displacement, velocity, and acceleration vector, and the angle. Okay, so this is correct. Then the second case, omega is given, so same way you need to draw, because it is 0.5, so velocity vector will be little bit shorter, because 10 will be the amplitude for displacement, 10 into 0.5, that is 5, that's why it is shorter than this displacement vector. This velocity vector is shorter than this displacement vector. Then again it will be 10 into 0.5 into 0.5, that is 2.5 will be the magnitude of this acceleration line. Okay, and it will be opposite to displacement. Here you should show the angle also, pi by 2 and pi by 2. I think by this problem you will be able to understand, okay, the concept of this equation. Okay, basic equation of this vibratory motion or simple harmonic motion. Okay, so I will be sharing this along with your slides. Okay, about this vibration. So okay, dear students, so if uh, okay, let us take another example also. I think it is there in my slide. Yeah. So you can see a harmonic motion has an amplitude, capital A is given 0.20 centimeter and a period of 0.15 second, capital T. This is capital T. So determine the maximum velocity and acceleration. So how will you find the maximum velocity and acceleration? What was our equation? X equals to capital A sine omega t. Okay, so when sine value is having maximum value, when it is 1, okay, so maximum value of amplitude will be how much? X equals to a, because a is what? It is the maximum amplitude, okay, maximum displacement from the mean line. So to find out the maximum velocity, our equation was what? X dot equals to omega a sine omega t plus pi by 2. But sine omega t plus pi by 2, that should be 90 degree, okay, or sine value will be 1. So what is the coefficient in front of this sine function? That is omega a, isn't it? So maximum value of this velocity will be, if you put it in the formula, x dot equals to a omega sine of omega t plus pi by 2, then it will be omega a, okay, or a omega. So to you need to put out the value of omega. So omega you need to find out by this given values. Omega equals to 2 pi by t, okay, so 41.89 radian per second. So x dot maximum value will be this one, okay, omega n. And for acceleration, what was the equation? So x double dot equals to omega square a, or a omega square sine omega t plus pi, okay. So sine value will be 1 when x double dot will be maximum, so omega square a will be the coefficient. So in this present in this equation, if you just put the value of omega, so you will get the maximum acceleration of this particle, okay. I think all of you have got the concept. So if you have any doubt, so you can ask. Okay, anyone, if you are having any doubt, you can ask. Let me check the comment box. Okay, is there any doubt or query you want to ask? Avinash, Raghav, Bhaskar, Champailar, Maren, Milo, Ansuman. Manas, how are you? Manas? Okay, so thank you, dear students. So we will meet in the next class. Okay, now you can leave this meeting.
Thank you, sir.